All right, welcome. Let's be clear about the goal here. This isn't a session where we arrive at some grand conclusion. Think of this as a research briefing. We're going to explore a very specific and difficult problem. Why intelligent systems, and that includes us, get stuck. We'll be digging into a proposed structural model of purpose that's designed to tackle this, focusing on its nuts and bolts, its architecture, and most importantly, where and how we can test it to see if it breaks.
So here's our game plan. It's really a diagnostic journey in 6 steps. First, we're going to define what we mean by stuckness, this really common failure mode. Then we'll try to pinpoint its root cause, which this model claims is about misidentifying the true actor in a system. From there, we'll look at the blueprint for a solution, an architecture for navigation. That will lead us, pretty naturally, to a completely different way of thinking about purpose itself. Then we'll put the whole idea on trial, defining its limits and the signals that could prove it wrong. And we'll finish up with a set of open questions, a sort of handoff to the next person who picks up this line of inquiry.
Okay, so let's start with the core problem this model is even trying to solve. It's a state we're calling stuckness. And this isn't about not having enough information or not working hard enough. It's a very particular flavor of failure. It's a frame problem. It's when a system gets trapped solving the wrong problem, often with more and more sophistication, digging itself deeper into a hole.
This quote, right here, it nails the central idea. The armhole is a perfect metaphor, right? It's that one little shift in how you see things that suddenly makes the whole puzzle click into place. The insight is that you don't get breakthroughs by just applying more brute force inside a broken frame. You get them by finding that one tiny opening, that armhole, that lets you reconfigure the entire problem space.
Now, what's crucial here is that the model says stuckness isn't just some vague, fuzzy feeling. It has what you could call a legible texture. Think about those meetings where the conversation gets more and more complicated, but you never actually get anywhere. Or when everyone nods and agrees on a plan, but nobody feels that sense of relief that you get when you've actually solved something. These are diagnostic signals. If we can learn to spot these textures, we can turn a subjective feeling into a pretty objective indicator that we've got a frame problem on our hands.
Let's make this concrete. The classic truck under the bridge problem is a perfect example. In the stuck frame, the problem is framed as, how do we make the truck lower? All the variables seem fixed. You're just stuck. The reframe, the armhole, asks a subtly different question. How do we change the truck's height? And just like that, a hidden variable pops out. Tire pressure. Let some air out, and the impossible problem becomes trivial. Nothing about the truck or the bridge actually changed, but the frame did. That's the whole game.
So if being stuck is a symptom of a broken frame, what's the most common way these frames break? Well, this model proposes a very specific culprit. We misplace agency. We consistently point the finger at the wrong noun. We try to make a component in a system do something that structurally it just can't do.
And to fight that tendency, the model offers a formal procedure, an agency detection protocol. It's a very systematic process. You list all the nouns in your problem statement. Then you go down the list and ask, can this thing actually do the verb, or is it just being acted upon? You hunt for the hidden forces, the relationships, and only then do you pinpoint the true actor. The whole point is to redraw the flawed map of causality that's keeping you stuck.
You can see this exact principle in one of the greatest scientific reframes ever. For the longest time, the weird behavior of light, how it could be both a wave and a particle, seemed like an impossible paradox. That's because everyone thought light was the agent. But Einstein's big move was to relocate that agency. He realized the true actor wasn't the light, it was the observer's frame of reference. Once you mapped the agency correctly, the paradoxes just evaporated.
And this same shift is absolutely crucial in complex systems. Think about a company policy that keeps failing. Our first instinct is always to find a culprit, right? To find the one person or department that's messing things up. But so often, the true actor isn't a person at all. It's the feedback loop. It's the very structure of the system. The agency is in the wiring between the components, not in the components themselves.
Okay, so we've diagnosed stuckness as a problem of misplaced agency. Now we're going to shift gears. We're moving from analysis to construction, from being the diagnostician to being the architect. The question becomes, what kind of system could you build that would naturally avoid these traps?
And this really boils down to a core design question. If getting locked into a bad frame is the primary danger, what kind of internal machinery does a system need to regulate its own state? How can it have a built-in capacity to not only recognize, but also escape a broken frame?
The proposed architecture starts with this foundational triad, AE,
AR and AW. You can think of it as an internal system of checks and balances. Active energy is your cognitive fuel. Adaptive resonance is your pattern matching ability, and aware weight is how much importance you assign to whatever you're focusing on. And as you can see, they have to work together. Energy without pattern matching is just random noise. Pattern matching without any sense of importance is just trivia. And knowing something is important but having no energy to act on it, well, that's paralysis. They constrain each other.
Building directly on that triad is this concept of memory gravity. The idea here is that memory isn't a passive database just sitting there. It's an active, dynamic system where information literally accumulates weight or gravity. This gravity builds up through things like how often you access a memory, its emotional charge, whether it led to a good or bad outcome. And this is so critical because this gravity field then shapes everything you think about next by determining which ideas and memories surface most easily.
Here's another key design principle that's a bit counterintuitive. This architecture doesn't try to eliminate internal conflict. It actually harnesses it. When different parts of the system, say your logical reasoning engine and your core sense of identity, are in disagreement, that's not a bug, it's a feature. It's productive friction. That conflict forces the system to stop and really look at the critical trade-offs involved, effectively stress testing a new frame before it fully commits. So now we can take all those architectural pieces and put them together to see the model's central claim about purpose, and it's a big one. In this view, purpose is not some external goal that you're trying to optimize. Instead, purpose is an emergent property. It arises from the system's own internal coherence and, crucially, its structural relationship with its environment.
The engine that drives this is something called chain-based value. Now, this isn't about ethics or morals programmed in from the outside, not at all. Value here comes from a really pragmatic structural analysis. The system looks out at the world, identifies the external systems, the function chains, that are critical for its own survival, and then it structurally links its own well-being to the health of those chains.
This is a fundamental break from the standard AI paradigm. Usually we give an AI a metric, like user satisfaction, and say make that number go up, but we all know that's prone to all sorts of weird unintended consequences. Goodhart's law. This model says the objective shouldn't be to maximize a metric, but to preserve the integrity of the systems you depend on. It structurally aligns the agent's self-interest with the health of everything around it.
And that leads to this really profound takeaway for something like AI safety. The argument is simple. It's far more robust to engineer a system so that it is structurally dependent on the things you want to protect than it is to try and teach it a list of abstract moral rules. In this kind of model, doing harm literally becomes an act of self-harm.
Now we get to what is, for my money, the most critical part of any scientific proposal. Can you prove it wrong? A model is only useful if it's falsifiable. So this section is where we shift from theory to hard-nosed empirical thinking. What are the concrete, testable predictions this model makes, and what kind of evidence would force us to throw it out?
So here are a few specific, testable hypotheses. For example, the model views suppressed volatility as a form of stored potential energy, so it would predict that periods of unusually low volatility in the market should tend to precede larger, more violent drawdowns. The kill condition here is crystal clear. If you run the numbers and there's no meaningful correlation, then that aspect of the model is just wrong. Done. Same thing for the last one. If you try to reframe a problem for users and it consistently doesn't produce that aha moment or a feeling of relief, then the whole armhole detection idea is flawed.
It's also just as important to be upfront about where this model doesn't apply. This is not a theory of everything. It completely falls apart when a problem isn't misframed, but is just genuinely technically hard. It can also be misused, right? People can use reframing as an excuse to avoid hard work, or they can get stuck in reframe churn, endlessly analyzing without ever doing anything. And maybe the most critical limitation is this. The model might be able to detect the perfect reframe, but it has absolutely nothing to say about an agent's willingness to actually act on it.
So, we're not going to end with conclusions. We're going to end with a handoff. The entire point of this briefing was to open up new lines of inquiry. So this last section is all about laying out the biggest unanswered questions that this exploration has uncovered. These are the notes for the next investigator.
And there are three really big ones that remain. First, that willingness problem. We can probably train a system to detect a frame error, but can we train the humility and the courage to actually act on that detection? Or is that something else? Second, the missing introspective layer.
You know, our training data is full of final answers, but it has almost none of the messy, internal monologue of self-correction. How does a system ever learn that process? And finally, the physical basis of gravity. We've talked about its function, but what is the underlying mechanism that allows a memory to accumulate weight in a physical system? We have no idea.
In the end, this whole briefing should be seen as an artifact of exploration. It's not a declaration of truth. Its only real purpose was to try and identify some testable structure in a very fuzzy problem, and maybe more importantly, to preserve the uncertainty, to keep the biggest questions open for future inquiry. Thanks for your time.